The sun looks the same as it did yesterday. It won't always. The one star we treat as unchanging has a violent side we almost never see. Your power, your phone, the money that only exists as numbers on a screen. Every piece of it assumes one thing, that the sun stays quiet. On September 1st, 1859, the sun stopped being quiet. And we survived that one for a single reason. None of this had been built yet. No power grid, no satellites, nothing a solar storm could reach in and break. That morning, an amateur astronomer in England watched the surface of the sun tear open with light. 17 hours later, telegraph wires across Europe and North America began to spark, and some of them caught fire. By the end of this, you'll understand three things: how big a solar storm can get at its worst, how often the sun does this, and the honest answer changed only last year, and why even now, with everything we've built, we could not stop it. And there is one storm you have never heard of. Not the famous one. A storm buried in the rings of ancient trees that makes 1859 look like a warning shot. And the record says it was not a one-off. To feel the danger, you need one thing in your head: a ladder. And you need to watch it climb. Start at the bottom. March 1989. A solar storm reaches the power grid of the Canadian province of Québec, and 6 million people lose electricity in 90 seconds. That's the small one. That's the storm we have already lived through in the age of electricity, and it barely made the history books. One rung up, 1859. Carrington storm. No power grid to bring down yet, but strong enough to set telegraph offices on fire and throw the northern lights as far south as the Caribbean. And then the top rung, the one almost nobody talks about. A storm we never caught with instruments, because there were no instruments. We found it written inside trees, more than 1,000 years later. We'll climb to it. Keep those three in mind: Quebec, Carrington, and the thing in the trees. Every minute from here we go up. Space weather forecasters grade these storms on a scale that runs from G1 to G5, the way we grade hurricanes. Quebec was driven by a G5, the top of the scale. Carrington would have run clean off the end of it. And the thing in the trees records a blow the scale was never built to measure. His name was Richard Carrington, and he was not looking for the end of the world. He was a wealthy young Englishman who had built his own observatory to do one quiet thing: draw the spots on the sun morning after morning. At 11:18 on the morning of September 1st, 2 points of blinding white light erupted from the group of spots he was tracing. He ran to fetch a witness. By the time he was back, it was already fading. It had lasted about 5 minutes, and he had become the first human being to see a solar flare. Carrington was careful. He wrote down what he saw, and he did not overclaim. Because at the time, the idea that the sun could reach across 93 million miles and touch the Earth was close to laughable. 2 camps had argued about it for years. One said the sun and Earth's magnetism were linked. The other, led by some of the most respected physicists alive, said that was superstition dressed up as science. 17 hours later, the argument ended. The aurora, the northern lights, burned over Cuba, over Hawaii, over Colombia. In the Rocky Mountains, gold miners got up at 1 in the morning and started cooking breakfast because the sky was bright enough to read a newspaper by, and in the telegraph offices the machines turned on the men who ran them. Sparks jumped off the keys. Paper burst into flame. Operators in Boston unplugged their batteries and found the lines still worked, carrying a current that was coming from the sky itself. Think about that. For a few hours, the wires were powered by the sun, and in England, at the Kew Observatory, the delicate magnetic instruments that a scientist named Balfour Stewart used to track the Earth's field were driven clean off their charts. The planet's own magnetism was bending, pulled by something 93 million miles away. The camp that had called the Sun-Earth link superstition went quiet. There was ink on paper now, and the ink agreed with Carrington. Here is what had happened to Carrington's sun, because a solar storm comes in two waves, and the second is the one that does the damage. The first wave is light. When the sun flares, the burst of radiation crosses 93 million miles in 8 minutes. You cannot outrun it, and you cannot be warned about it, because it arrives at the exact instant as the light that would carry the warning. It reaches your side of the planet before anyone can say a word. It blacks out radio across the entire daylit half of Earth in the same instant. Pilots and ships going quiet mid-sentence. The second wave is matter. The sun throws off a coronal mass ejection, a cloud of electrically charged gas that can weigh 1 billion tons. Picture a mountain launched off a star, moving at over 1 million miles an hour. That cloud usually takes 1 to 3 days to cross to us. Carrington's cloud made the trip in about 17 hours, one of the fastest ever recorded, because an earlier eruption had swept the path clear in front of it, like a snowplow for the one behind. And when it struck Earth's magnetic field, it did not bounce off. It pressed down through it, and it made the whole field shudder. That shudder is the thing that hurts us, because in the century and a half since, we have wired the entire planet for exactly the kind of current a shuddering magnetic field creates. So let's climb a rung and stop guessing. What happens when a storm like that meets a modern grid? We don't have to imagine it. We have the receipt. March 13th, 1989. 2:44 in the morning. A coronal mass ejection slams into Earth's magnetic field, and the field starts hunting for long wires to drive current through. Quebec's grid is one enormous wire strung across 1,000 miles of rock. The induced current floods in. Protective relays trip like dominoes. And in 92 seconds, less time than you've been watching this chapter, the entire province goes black. 6 million people in the dark, at minus 15 degrees in a Canadian March. Hospitals fall back on generators. The Montreal Metro stops. Traffic lights die across the city. It takes 9 hours to bring the power back. The damage ran into the hundreds of millions. And Québec spent the years after spending billions to harden the grid so the same failure could never repeat. And remember, that was the bottom rung. But here's the detail that should stay with you. That same night, 1,500 kilometers away in New Jersey, a huge transformer at a power plant quietly overheated and cooked itself from the inside. It wasn't in the blackout zone. It wasn't anywhere near Quebec. The storm reached out and found it anyway. In 1989, only a handful of things melted. Fortunately, for now. Let me put the mechanism plainly, because it is the whole story, and it is quieter than you'd expect. A solar storm does not strike your house like a bolt of lightning. When the storm shoves Earth's magnetic field back and forth, that moving field pushes a slow, steady current into every long conductor we have ever built. Power lines, oil pipelines, railway tracks. Engineers have a bloodless name for it: geomagnetic induced currents. Our grid runs on alternating current, power that flips direction 60 times a second. What the storm feeds in is direct current, one steady push, bleeding into a system that was never designed to carry it. And it goes straight for the one part we cannot quickly replace, the great transformers at the heart of the grid. Each one is the size of a house, weighs hundreds of tons, and is custom built to order, often from a factory on another continent. Order a replacement today and it may not arrive before the next winter. We keep almost no spares. Lose a dozen of them in one night, and you are not waiting on a repair crew. You are waiting on a factory to build machines that take a year apiece, while the region they fed has no power to run its water pumps. its fuel pumps, or its refrigeration. The blackout stops being an inconvenience somewhere around day 3. So here is the question that turns all of this from history into a warning. Which world is more exposed to a solar storm? The one from 1859, with a few strands of telegraph wire, or the one you're living in right now? The answer is you, and it is not close. In 1859, a solar storm had almost nothing to break. Today, it has all of it. Start above your head. The GPS that guides your car. The timing signal that stamps your bank transfers. The clocks that keep the internet in sync. They all run through satellites. And satellites sit above the atmosphere that shields the rest of us, out in the open where the storm hits first. That timing signal is invisible and everywhere. It stamps every card payment, syncs every cell tower, holds the grid itself in step, bend it, and 100 systems that never once look at the sky start to fail at the same moment. In February 2022, a fairly weak solar storm warmed Earth's upper atmosphere enough to thicken it, and dragged about 40 brand new Starlink satellites back down to burn up before they reached their orbit. A weak storm. 40 machines, gone in days. It reaches the ground, too. In 2003, a run of solar storms we now call the Halloween storms knocked out power to 50,000 people in southern Sweden and damaged transformers as far away as South Africa. Airlines already reroute flights off the polar routes during a solar storm, because up there the radiation climbs and the radios go silent. So picture the 1859 storm, not the one in the trees, the merely historic one, arriving tonight. One study run by Lloyd's of London put the cost to the United States alone at somewhere between $600 billion and $2.6 trillion. That is close to 1/10 of a year's entire economy. From one bad night, on a star you will never touch. And the dollars are the easy part to picture. The hard part is the first 72 hours. No water pressure above the 3rd floor. No card readers. No fuel pumps, which means no way to move the trucks that carry the food. All of it, from one storm you would only notice as a beautiful sky. And twice, in living memory, the only thing standing between us and catastrophe was the calendar. The sun fired a shot, and we happened not to be standing where it landed. That is luck, not planning, and luck runs out. August 1972. A solar flare so violent it set off magnetic sea mines the U.S. Navy had dropped in the waters off Vietnam. The storm detonated them from 93 million miles away. That flare landed in the narrow gap between 2 Apollo moon missions. Had it come while astronauts were crossing to the moon, outside Earth's magnetic shield, the radiation dose could have killed them. We didn't plan around it. We weren't up there that week. NASA studied that flare for years afterward because it broke their models. The particles arrived in minutes, not the hours the textbooks promised. Then July 2012. A storm every bit as strong as Carrington's tore off the sun and swept across Earth's orbit, through the exact patch of space our planet had rolled through 9 days earlier. We missed a direct hit by 9 days. One physicist, Pete Riley, later ran the numbers on how often storms this size come around, and put the odds of a Carrington-class strike at roughly 12% per decade. 12%. That's not a distant asteroid. That's a coin you keep flipping. Fortunately, it landed our way. For now, and if all of this still feels like something that happens to other people, remember what happened last year. Over your own street. In May 2024, the strongest solar storm in more than 20 years reached Earth. Scientists named it the Gan-un storm. People who had never left their home state watched the aurora ripple over their backyards, over Florida, over Mexico, over places that had not seen it in living memory. Millions of us photographed it and called it beautiful. It was beautiful. It was also a near miss wearing a costume. Out of sight of the crowds, farmers across the American Midwest lost the GPS guidance in their tractors in the middle of planting season. And satellites had to fight to hold their orbits. And here is the part that should unsettle you. The Gannon storm was strong enough to paint the sky over Mexico and still break equipment across a continent. And it was nowhere near a Carrington. It was not even on the same rung of the ladder. It was a soft knock on the door. The sun knocked. We took photographs and we posted them online. That is roughly the level of attention we are paying to the thing waiting at the top of the ladder. Which brings us, at last, to that top rung. Here is where it stops being history and starts being something older than any record a human ever thought to keep. To reach the top of the ladder, we have to read the storm straight out of the trees. Every year, a tree lays down a ring. And in the year 774, trees on every continent laid down a ring with a strange mark inside it, a sudden surge of a rare, heavy form of carbon called carbon-14, far above any normal year. Not in one forest. In Japan, in Europe, in North and South America, all at once. That surge is the fingerprint of an enormous blast of radiation striking the atmosphere. And ice cores drilled from Greenland and Antarctica carry the same year, the same wound in a different chemical. Beryllium and chlorine. 3 separate records. 1 event. The leading explanation is a solar storm, one that may have been several times stronger than anything we have ever measured with a machine. We call these Miyake events, after Fusa Miyake, the researcher in Japan who first found the mark in 774. Now I have to be straight with you, because this channel lives on it. The spike in 774 is a hard fact. That the sun caused it is the best explanation we have, not a closed case. And exactly how big it was, scientists are still arguing. But here is what is not in question. It happened again in 993. That second spike is so precise that archaeologists used it to date a Viking settlement in Canada to the exact year, 1021. This is not a one-time freak of nature. It is a pattern with a rhythm we are only beginning to read. There is a third mark, older still, around 660 BC. 3 confirmed strikes written into 3,000 years of wood and ice. And not one of them landed on a world that runs on electricity. We have never once taken a punch that size with the lights on. A Miyake scale storm today would not be a blackout you wait out with a flashlight. It would be the kind of blow that resets how an entire continent lives for a year or more. That is the top of the ladder. And it is not science fiction. It is in the wood. And in 2024, that 1,000-year pattern in the trees was handed a hard number, one that should stop you cold, because it came not from our own sun, but from tens of thousands of stars that are nearly its twins. For decades, most astronomers assumed our sun was too old, too settled to throw a true monster. A superflare, a flare hundreds of times stronger than anything in our written records, was something wild young stars did, not a middle-aged star like ours. It was a comforting assumption. It was also a test that no one had ever run on enough stars to trust. Then a team led by Valery Vasilyev at the Max Planck Institute in Germany did something simple and merciless. They pulled the records from the Kepler Space Telescope, which had stared at other stars for years, and they picked out the ones that are near twins of our sun. Same temperature, same steady rhythm. And they counted the superflares. 56,000 sun-like stars, and the monster flares showed up far more often than anyone had dared to expect. Their finding published in the journal Science. A star like our sun produces a superflare roughly once per century. A flare that size would carry the energy of billions of our largest hydrogen bombs, unloaded in minutes. Say that again. Not once every 10,000 years the way we used to comfort ourselves. Once per century. That is inside a single human lifetime. And no one alive today has watched the top of that ladder arrive with the lights on. So the real question was never whether a big solar storm is coming. The trees answered that. The record answers that. The question is how much warning we would get. And this is the part that keeps grid engineers awake. We have two spacecraft, called Discover and AC, parked about 1 million miles closer to the Sun, at a spot named L1. When a coronal mass ejection sweeps past them, they take a reading of what's inside it. That reading is our alarm bell, and that alarm gives us somewhere between 15 and 60 minutes. Less time than this video. That is the entire window in which grid operators would have to drop the load, disconnect the most exposed lines, and shield the transformers. For a whole planet at once. Worse, we cannot reliably see the big one coming before that. We can watch a sunspot group swell to the size of dozens of Earths. We can say the odds are rising, but we cannot point at a date because the physics of when a flare snaps is still beyond us. The Sun does not file a flight plan. It has handed us a warning measured in minutes, and on the biggest one, a head start of close to nothing. Solar cycle 25 and the Sun's current 11-year heartbeat most likely peaked in late 2024. That sounds like the danger easing. Except some of the worst storms on record hit on the way down. Here is the part almost nobody tells you, and it is the honest one. This is not hopeless. It is unfinished. We already know how to protect a grid. There are devices that block those induced currents before they reach the transformers. Operators who get a warning can shed load and pull the most vulnerable lines offline in time. After the 2003 storms, and again after 2015, governments wrote real plans for exactly this. Reserve transformers staged near the biggest cities, grounding blockers on the lines most exposed, a forecast center with the authority to tell operators to power down before the cloud lands. The problem was never the physics. It's that this protection is installed in patches, not across the whole grid, because it costs money now to defend against a storm that has not come yet this year. We are gambling on the Sun's patience, so let me give you the honest ledger. All in one place, the way I'd want it given to me. Proven. The Sun has hit Earth hard more than once, and our grid is wide open to it. Strong evidence. Superflares strike Sun-like stars about once a century. Still open. Exactly how large the Sun's worst can grow, and precisely when the next one lands. None of that is a reason to panic. All of it is a reason to finish the wall before the flood. So, are we overdue? It is the wrong word, and it is the one everyone reaches for because it makes a random star sound like a train running late on a timetable we can read. The Sun is not a clock. It does not owe us a storm on a schedule, and it does not spare us because we had one recently. Every calm year is not the danger passing by. It is the danger holding its breath. We have spent more getting ready for storms we can watch march across a weather map than for the one storm that could take the map itself down. We have built an entire civilization that only works while the Sun stays calm. And nobody asked the Sun. Look at the ladder one last time. Québec, which we lived through and forgot. Carrington, which we would feel for years. And the thing in the trees, which we have never once faced with the lights on and the whole world plugged in. We are standing at the bottom of it, looking up, quietly hoping the next one stops where the last one stopped. Tomorrow the sun will rise, and it will look exactly the same as it did today. The same as it looked the morning Richard Carrington sat down to sketch it, hours before the wires caught fire. That was always the trick. The warmth you can feel on your face is real, and it is also the thinnest possible skin over a star that has, more than once, reached across the dark and struck this planet hard enough to leave its mark in the wood of living trees. It has done this before more than once, and it left the proof in stone and wood and ice. It will do it again. The only things we don't know are the date and whether the lights will still be on when it comes. So the next time someone calls the sun the one thing you can count on, remember what it wrote into the wood of the trees. The sun looks the same as it did yesterday. It won't always. That's as far as this one goes, but the edge always moves. This is a philo. Subscribe, drop a like if it earned it, and your next one's on screen now. I'll meet you a little further out.